Okay, everyone, so we're going to talk right now about molecular compounds. So we're moving away from ionic and we're looking at now elements that share electrons with one another. Now, we did talk about molecular compounds at the beginning of this section of the course, where we started talking about types of bonds that could be made. So we're just going to review a lot of the things we may have already said. So molecular compounds, sometimes molecular is also known as covalent. So if you see covalent compound or molecular compound, they mean exactly the same thing, okay? So a molecular compound is made as a result of sharing electrons between atoms, so not transferring. So you don't have the give and take that ionic has, it's a sharing. So what ends up happening is the orbits of the atoms come close enough together that basically the electrons can move from one orbit to another. So really both atoms have that electron in their orbits. And of course the bond that's produced is called a covalent bond. So this is just a very simplified kind of picture to show you what's happening. So imagine here we have two hydrogen atoms, so meaning there's only one electron in that first orbit. So when they come together, you're going to see, if you watch this long enough, that the electrons are able to flow between both. So these two electrons are being shared with each other. So remember that ionic compounds is when you have a metal with a non-metal, okay? But when we're dealing with molecular compounds, you have two or more non-metals coming together. And keep in mind, hydrogen is also part of that. So something like water, right? H2O. We have hydrogen and oxygen. Those are non-metals. So we know that those are going to share their electrons and not transfer them. So what are some properties? So when we talked about ionic compounds, we talked about ionic properties. Molecular compounds are quite different. So if you remember, ionic compounds are always a solid at room temperature. Molecular compounds come in a variety. So you can have solids, liquids, or gases, so pardon me, that make up molecular compounds. So some examples are down here. So for example, glucose, which is basically sugar, is a solid at room temperature. Water, of course, we know is a liquid at room temperature. And gasoline is actually also a liquid at room temperature. So an example of something that would be a gas at room temperature could be nitrogen gas, right? Or we could also be talking about carbon dioxide, right? So carbon dioxide is two non-metal elements, right? Carbon and oxygen. And we know that they are going to share their electrons, but it's a gas. So you have all different types of states that can exist. It's not like ionic compounds. If you remember, ionic compounds have very high melting and boiling points. Molecular compounds have relatively low melting and boiling points. So if you remember, we were talking about ionic compounds, they can be, over 800 degrees, which is very high if you compare it to something, let's say, like water, which is 100 degrees. Or the melting point, I should say, is 0 degrees, right? So it's not a matter of like a big number or a small number, but like comparing the two types, molecular compounds are always lower than ionic compounds. And in terms of conducting electricity, molecular compounds are not electrolytes. So meaning, if you were to dissolve them in water or melt them down, they do not conduct electricity, whereas ionic compounds do. So these are the Bohr-Rutherford diagrams for the atoms that make up water. Okay, we will be doing similar to ionic compounds. Remember I showed you that with some pictures with Bohr-Rutherford, but then we drew it with a Lewis dot. The same thing is going to happen here. So I'm just going to show you a diagram of the Bohr-Rutherfords for this. And actually, oh my goodness, I just realized this picture is wrong. This should be 8 protons and 8 neutrons. They had it written as another, hydrogen. Jeez Louise. Anyway, I'm going to show you this picture for the Bohr-Rutherfords, but then I'm going to show you what I expect, which will always be the Lewis dot. So here we have 2 hydrogens and an oxygen, and we can tell how many we have by looking at the chemical formula. So you can tell oxygen has 1, 2, 3, 4, 5, 6 valence electrons. It needs 2 more. Each hydrogen has 1 and needs 1 more in order to have its full shell. Remember, the first shell can hold a maximum of 2. So what it would look like once it's all overlapped, here's the correction, once it's overlapped is something like this. So imagine that this red one belonged to this hydrogen, and this one belongs to, let's say, this hydrogen. So all the blue dots, 1, 2, 3, 4, 5, 6, are oxygen's valence, and then hydrogen has its 1 and 1. Now, the overlap here is to show you, similar to that animation, right? These electrons can really move between these orbits now. So it satisfies both of the atom's requirements. So this type of bond is called a covalent bond. So that's why sometimes molecular compounds are called covalent compounds. It's because it has a covalent bond. So this is talking about the sharing of electrons. All right, so let's get to drawing. So we're going to draw using Lewis dot diagrams. So again, it's kind of like the best way to learn this is to look at examples. So the instructions are here. We are going to draw the Lewis dot for each atom. We are then going to connect the electrons that are not already paired. And we're going to draw a circle to do that. And then we're going to change the circles into dashed lines, and we are going to continue drawing any electrons that have to be there. Each dashed line represents 1 covalent bond. Okay, so that probably didn't make a whole lot of sense, but don't worry, we're going to go through some examples. All right, so for the first one, we have NH3. So we know, first of all, when you're looking at these, you have to stop and think, is this ionic or is this molecular? Because these are nonmetals, I know I'm going to be sharing electrons. So how we're going to do this is we always start by drawing the Lewis dot for each of these elements. So I have 1 nitrogen and I have 3 hydrogen. And hydrogen has only 1 valence electron. It doesn't really matter where you draw them to start. Eventually we're going to connect these and then redraw it out down here. So, do you see how these electrons are paired up already? If you remember, electrons go in pairs when we have a full 8 of them, like 2, 4, 6, 8. So the ones that are already in a pair cannot be shared. It's only the electrons that are solo that can share with another solo electron. So what's going to happen here is this electron from nitrogen will share with this hydrogen electron. How we show the sharing of electrons is we basically draw like a circle to show that they are like now connected. So like this electron and this electron are being shared. And then we would continue. So this electron is alone, so is this electron. So we now have paired up these solo electrons. And then we have 1 more pairing here. Okay, so another connection. So at the end of this, you should not end up with having any electrons by themselves. So like the number of atoms that are in this molecule should always work that no atom is left kind of hanging. Every lone electron has to be paired up. So this picture we did right here is the formation of this molecule. So if you remember ionic compounds, it was the arrow picture. This is now showing the formation of a molecular compound, the sharing. So let's look at the final picture. How would we draw the final compound? So we always draw in the electrons that we did not touch. So this nitrogen has those 2 electrons, that is staying as is. But for every circle we drew, we are going to replace it with a line. So this line is representing this shared section. We're going to draw another line for my other hydrogen. So again, this line is representing this shared section. And then we have another hydrogen being shared on this side. So that's what this part here. Each dashed line represents one covalent bond. So this one line represents one covalent bond. So meaning one electron from hydrogen is being shared with one electron from nitrogen. And that happens 3 times. So this is the formation. This is the final compound. So if the question ever says, draw the formation and the final compound, that means I want to see both of these. Over here, Br2. So again, we have now 2 bromines. And each one, it's in group 17. So each one has 7 valence electrons. Ooh, these ones are far apart. And what ends up happening is you have 3 sets that are already paired up, but there's one by itself on one bromine and one by itself on another bromine. So what ends up happening is those 2 solo electrons are being shared. So the final compound for this, we have 1 dashed line in the middle because we have 1 being shared with each one. And remember that the electrons we don't touch should still be in our final picture. So just like here, this nitrogen set we kept, all of these bromine sets should still be there in the final picture. All right, so double or triple bonds. I'm going to have you try out a few more on your own when after I go through these examples. Okay, so a double bond essentially means that you are now sharing 2 sets of electrons between atoms. So over here, do you see how we have 1 circle being drawn, 1 dash line? This is 1 set of electrons being shared. 1 from hydrogen, 1 from nitrogen. So if you were to have a double bond, there is 2 pairs of electrons that are being shared. So your final picture actually will end up having 2 dash lines. A triple bond is when you have 3 pairs of electrons being shared. So you would have 3 dash lines. So why would you ever want to make more than 1 dash line? So remember, the whole point of this is to create a stable octet, like to have the full valence shell. So sometimes you need to gain, or I should say not gain, poor choice of words, you need to share more than 1 in order to reach the full 8. So let's check this out. All right, carbon dioxide. So we have carbon, 1, 2, 3, 4. It's in group 14. Oxygen has 6. And then we have another oxygen that also has 6. Okay, so carbon can share 4 electrons because see how they're all alone. Oxygen can share 2, and this oxygen can share 2. So maybe you can already see kind of what's going to happen. Remember that the ones that are already paired up cannot be touched. So this 2, this 2, this 2, and this 2. But I can share 1 electron from the oxygen with one of the solos on carbon. And I'm going to do another one because I have 2 that are solo, not just 1. The same thing will happen on the other side. Look, we have 1, 2 available, 1, 2 available. Whoop, sorry, that dot should be there. And there we go.